Leetcode 79 word search. They classified it as medium, but I would say it's one of the more difficult mediums, and definitely don't get discouraged if you start doing this problem and find it difficult, since it really is difficult and you need to understand backtracking very well in order to solve it. And here is the description. Given an m times n grid of characters called board, so m is the number of rows, n is the number of columns. Here we have one example, and of course, because those are different, it can have a different amount of rows and columns, a different number of rows and columns. And a string word. So those are the two inputs. First is board, and in Python is list of strings, but this inner string, this very inner string, is of course a single character. So each cell in our grid or on our board stores single character, and the word is a string which consists of multiple characters, or can consist of multiple characters. And we have to return true if word exists in the grid. And what does it mean that word exists? Let's just emphasize that the output is Boolean, and here there is additional explanation. The word can be constructors from matter of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. So no neighbors through diagonals, only up, down, right, and left. Those are our 4 possible neighbors. And the same letter cell may not be used more than once. Of course, we cannot reuse one cell more than once. And we could have, for example, such a case that all the letters are here, but they are not in adjacent cells, or not in correct order. And in this case, we cannot return true. We have to return false. So we have to keep track of the letters, but also of the order, and only check adjacent cells. And here's an example. We have following board. Here's ABCE, then SFCS, ADEE, and the word is ABCCED. And there is a possibility of constructing it in the following way. They marked it with yellow, and of course we can change directions. The only constraint is that the cells have to be adjacent, and in this case they are. There's a second example for word C, and we don't learn anything new here. It's also there. And the third example is an example where there is no such word on the board, A, B, C, B. And for example, we have A, B, and C here. And if we could reuse B, then it would be okay, but we cannot, and that's why it's false. Okay, so let's copy that, and let's think about that backtracking, as I have already mentioned, and how to use it. That's our board. Yes, and we can like this. And our task is to find the word search. And the name of the game is backtracking, which basically works with recursion. And the most important part is to notice or to know ahead that 2D grids / boards / matrices and so on can be thought of as graphs. Those are also graphs. And each cell in our grid, this is for example a cell with A, this is another cell, is a node, and cells are nodes or vertices depending on which kind of terminology you're using. Nodes. And then connections to neighbors, like up, down, right, and left. There we have already mentioned that we cannot connect through diagonal. So diagonal connections are not allowed. We are not considering those as neighbors. Are our edges. So graphs basically consist of nodes and edges, and in our case cells are our nodes and the connections to neighbors are our edges, and we can traverse this graph using some graph traversal algorithms. And two obvious choices always are DFS and PFS. And in case of backtracking, even though we can still use BFS, I think DFS is more natural, and I usually prefer DFS. Yeah, and sometimes there are cases where BFS is more advantageous, mostly where DFS, due to its recursive calls, we can get Stack Overflow here. And in this case, we should use BFS, but that shouldn't be the case here. Yeah, and BFS basically goes along single path as deep as possible and backtracks. And BFS checks all the neighbors layer by layer. Yeah, and right now we will use, this case we'll use DFS, which I usually prefer for such problems with boards. Yeah, and how can we use it? Well, of course, we have to check each cell, but just one more thing before we go to that algorithm. Let's also write down the time complexity, which for both of them is V plus E. Yeah, where V is the number of vertices or nodes and E is the number of edges. But in this case, you can think about this in two ways. So you can think of this as a linear complexity if all the cells are like your base item on which to which you compare. Yeah, but in the case of the board, we can also think of like one side of being the base item, and in that case it would be like a quadratic because we have n times n or n times m, but we can use either n or n depending on which one is longer and make it bound by a quadratic complexity. But if we just think about the number of cells or the amount of cells, yeah, then it's still linear. Yeah, so that's like a more digression, but it's important to first of all know it in its general case, and second, here particularly for grids, how it scales. Yeah, so it's usually worth noticing for those kind of Leetcode like problems, since it's also necessary to explain during job interviews, and usually people study Leetcode just for the job interviews. Yeah, so don't get confused on that. And now about the algorithm itself. We have to check each cell, which for any grid or any board we can do using two loops, an outer loop and an inner loop, of course. And we can get each cell. An outer loop will keep track of the rows, and an inner loop will keep track of the columns. And then by getting both row and column, we can get any cell. Yeah? So we can iterate through the grid using nested loops. And then for each cell, start the search using DFS. Start the search for the word, how it was called, or the word called word, using DFS. Using DFS, and either we are lucky and we have found our word, and in this case we can terminate. If we found the word, then terminate with success. Otherwise, we have to continue, else continue, and that's it. That's the whole high-level algorithm. And of course, the hardest part is implementing this DFS for this particular case. Else continue. And if we iterate through all the cells and we haven't found the word yet, then by the end we return false. So, how to implement DFS here? That's the hardest question. And basically it will have three parts. First is success condition. Failure condition. And recursive call. So what is the success condition? The success condition will be met then when we have all the characters from the word already traversed. Yeah, so we have to keep track of how many letters we have traversed or how many characters we have already matched during our traversal. And if we matched all the letters, then it is success. That's the only possible option. Yeah. So keep track of the letters matched so far. If let's call it word index, this will be our counter for that. We can even use snake case for this to make sure that it doesn't get confusing. It refers to the thing that we'll put in the code. Yeah, if it's equal, if it equals the length or the number of characters of the word, then we can terminate with success. Failure is failure happens when failure happens if the cell that we are currently exploring has different character than corresponding char from the word on word index. Like this. That's one possibility of failure, and the other is when we go out of bounds. Yeah. So basically, the DFS will be going start in this cell, and we go as deep as possible in each direction. Yeah, and we can go outside of the board by going this as deep as possible. If we go out of bytes, then it's also failure. And the recursive call will be first, we will have to mark the current cell as visited. And then call the DFS on all 4 neighbors and increment word index by 1. That's it. And then unmark. Yeah, that's the backtracking part. And that's it. That's the whole algorithm. Yeah. So we have 3 options. Success condition. Our word index have already reached the length of the word. Failure condition. Either we have different character in the cell as the one that we should get from the word, or we go out of bounds. Otherwise, if it's not different, then it's correct character, and we can call all the neighbors. But we also have to prevent somehow to revisiting the same cell multiple times. Yeah? So that's why we mark it as visited, and then we on the backtracking we unmark the current cell and or mark it as unvisited again. And that's it. That's the whole algorithm. So basically, we go each cell one by one, then we go as deep as possible with DFS, and every time we check if using this word index, if the current cell has the same character as we expect from the word. If not, we terminate. If so, we continue with all its neighbors again. That's it. And if ever we have a success, then we also have success in this like outer algorithm, and we can terminate the whole program. That's it. So let's try to now implement. And first things first, let's create M and N, since they will be quite useful. M is the number of rows, and N is the number of columns. Then we will have our big DFS, for which we need I, J, 2 indices to identify the cell, and index inside the word index. And we will implement it in a second. And below we will have our loop, which will go for I in range M, through the whole board for each cell, and J in range N, all the rows, all the columns. And if DFS of I, J, and 0, we always start from 0. The first word index will be 0. Then return true, otherwise return false. So that part is easy. Now let's think about what's inside here. So the condition for success: if word index is equal to the length of the word, then we return true. First part of DFS is also easy. Now the second part, condition for failure: either we are out of bounds, so I is less than 0, or I is greater than or equal to M, or J is less than 0, or J is greater than or equal to N, or word on word index doesn't match with board on position I and J. So in this case, the failure and we return false. Now we can mark our board as visited. Yeah, we can put some character which for sure will not be part of the word, like this hash. And we will unmark it by the end. And now we have to call DFS on all the neighbors. So the first neighbor is the top, bottom, right, and left here, and increments the word index. -1. And here j -1 as well. And if any of them, by the way, returns true, or and the fourth option is or. Yeah, if any of them returns true, then we can return true here. And the same is not the same as for false. If we need just one of them returning true to be true, and most of them can be false. If all of them are false, then we return false. Let's see. First 3 cases work, and now let's submit. See all the cases. Yeah, and we are better than 80% when it comes to time, but only better than 20% when it comes to memory. That's because we keep in memory all those markers.